Choice problems at the national lottery drawings in Hungary. 5 numbers are selected at random from the set 90 braces. To win the main prize, one must guess all 5 numbers correctly. How many lottery tickets does one need in order to secure the main prize? This problem is an example of the last and most interesting kind of elementary enumeration problems, the choice problems. In these problems, we have to choose subsets of a given set. We will often require that the subsets have a specific size. The important difference from the previous 2 sections is that the order of the elements of the subset will not matter. For example, the set 1, 43, 52, 8, 3 and the set 52, 1, 8, 43, 3 are identical as subsets of 90 braces. The number of k-element subsets of n braces is of a pivotal importance in enumerative combinatorics. Therefore, we have a symbol and a name for this number. Definition 3.15. The number of k-element subsets of n braces is denoted n choose k and is read n choose k. The number n choose k are often called binomial coefficients for reasons that will become clear in Chapter 4. Theorem 3.16. For all non-negative integers k which is less than or equals to n choose k is equals to n factorial divided by k factorial multiplied to n minus k factorial. Proof. To select a k-element subset of n braces, we first select a k-element stream in which the digits are elements of n braces. By theorem 3.6, we can do it in n factorial divided by n minus k factorial different ways. However, in these strings, the order of the elements does matter. In fact, each k-element subset occurs k factorial times among these streams, as its elements can be permuted in k factorial different ways. Therefore, the number of k-element subsets is 1 over k factorial times the number of k-element streams, and the proof follows. Therefore, if we want to be absolutely sure to win at the Hungarian lottery, we have to buy 90 choose 5, which is equals to 90 times 85 times 88. Now, 90 times 89 times 88 times 87 times 86 divided by 1 times 2 times 3 times 4 times 5, which is equals to 4394926 tickets. If you do that, make sure you fill them out right. Definition 3.17. Let S, which is a subset, equals to n braces. Then the complement of S, denoted S to the C, is the subset of n braces that consists precisely of the elements that are not in S. In other words, S to the C is the unique subset of n braces that for all I in n braces satisfies the following statement: I in S to the C if and only if I is not in S. The following proposition summarizes some straightforward properties of the numbers n choose k. We choose to announce these easy statements as propositions since they will be used incessantly in the coming sections. Proposition 3.18. For all non-negative integers k which is less than or equals to n, the following hold. 1. N choose k is equals to n choose n minus k. 2. N choose 0 is equals to n choose n, which is equals to 1. Proof. When we set up a bijection f from the set of all k-element subsets of n braces onto that of all n minus k-element subsets of n, this f will be simplicity itself. It will map any given k-element subset S, which is a subset equals to n braces, into its complement S complement. Then, for any n minus k element subset T, which is a subset equals to n braces, there is exactly one S, so that f of S is equals to T, namely S is equals to T complement. So F is indeed a bijection, proving that the number of k-element subsets of n braces is the same as that of n minus k element subsets of n braces, which by definition means that n choose k is equals to n choose n minus k. 2. The first equality is a special case of the claim of part 1 with k equals to 0. To see that n choose 0 is equals to 1, note that the only zero-element subset of n braces is the empty set. We note in particular that 0 choose 0 is equals to 1, and that sometimes it is convenient to define n choose k even in the case when n is less than k. It goes without saying that in that case, we define n choose k equals to 0 as no set has a subset that is larger than the set itself. Example 3.19. A medical student has to work in a hospital for 5 days in January. However, he is not allowed to work 2 consecutive days in the hospital. In how many different ways can he choose the 5 days he will work in the hospital? Solution. The difficulty here is to make sure that we do not choose 2 consecutive days. This can be assured by the following trick. Let A1, A2, A3, A4, A5 be the dates of the 5 days of January that the student will spend in the hospital in increasing order. Note that the requirement that there are no 2 consecutive numbers among the AI and 1 less than equals to AI which is less than equals to 31 for OI is equivalent to the requirement that 1 which is less than equals to A1 less than A2 minus 1 less than A3 minus 2 less than A4 minus 3 less than A5 minus 4 which is less than or equals to 27. In other words, there is an obvious bijection between the set of 5-element subsets of 31 braces containing no 2 consecutive elements and the set of 5-element subsets of 27 braces. Instead of choosing the numbers AI, we can choose the numbers 1 less than equals to A1 less than A2 minus 1 less than A3 minus 2 less than A4 minus 3 less than A5 minus 4 which is less than equals to 27. That is, we can simply choose a 5-element subset of 27 braces, and we know that there are 27 choose 5 ways to do that. The trick we used here is also useful when instead of requiring that the chosen elements are far apart, we even allow them to be identical. Example 3.20. Now assume that we play a lottery game where 5 numbers are drawn out of 90 braces, but the numbers drawn are put back into the basket right after being selected. To win the jackpot, one must have played the same multiset of numbers as the one drawn regardless of the order in which the numbers were drawn. How many lottery tickets do we have to buy to make sure that we win the jackpot? Solution. We are going to apply the same trick as in the previous example, just backwards. We claim there's a bijection from the set of 5-element multisets. 1 less than equals to B1, less than equals to B2, less than equals to B3, less than equals to B4, less than equals to B5, less than equals to 90, onto the set of 5 elements subsets of 94 braces. Indeed, such a bijection F is given by F of B1, B2, B3, B4, B5, which is equals to B1, B2 plus 1, B3 plus 2, B4 plus 3, B5 plus 4. It is obvious that the numbers Bi satisfy the requirements given by 3.2 if and only if F of B1, B2, B3, B4, B5 is equals to B1, B2 plus 1, B3 plus 2, B4 plus 3, B5 plus 4, is a subset of 94 braces. Therefore, we need to buy 94 choose 5 lottery tickets to secure a jackpot. There's nothing magic about the numbers 90 and 5 here. In fact, the same argument can be repeated in a general setup to yield the following theorem. Theorem 3.21. The number of k-element multisets whose elements all belong to n factorial is n plus k minus 1 choose k. The following table summarizes our enumeration theorems proved in this chapter. Table 3.1 Enumeration formulae proved in this chapter. Permutations. If the parameters is n distinct objects, the formula will be n factorial. Permutations if the parameters is ai objects of type I such that the summations of ai summing with index I starting from 1 to k is equals to n, then the formula is n factorial divided by a1 factorial times a2 factorial and so on times ak factorial. For lists, if the parameters is n distinct object list of length k, then the formula is n braces with sub-index k, which is equals to n factorial divided by n minus k factorial. For the lists, if the parameter is n distinct letters, words of length k, then the formula is n to the k. For subsets, if the parameter is k-element subsets of n braces, then the formula is n choose k. For the subsets, if it's a k-element multisets with elements from n braces, then the formula is n plus k minus 1 choose k. Note: one of the most difficult of the exercises of this chapter is exercise 24. The first one to prove the formula given in that exercise was probably P. A. McMahon in 1916. The proof presented here is due to the present author. A high-level survey using commutative algebra of results concerning magic squares can be found in Combinatorics and Commutative Algebra by Richard Stanley, while a survey intended for undergraduate and starting graduate students is presented in Chapter 9 of Introduction to Enumerative Combinatorics by the present author.